So, so let's talk a little bit more about some data modeling. This is more the data ops piece.
Yeah.
We talked a little bit about it before, but it's the idea of inheritance and composition. And inheritance is used a lot in programming, but I think for data ops is really the context that we want to have for it here, in the same way with composition. And I think it's given us the ability. It's another one of these. I wouldn't call it a continuum, but it's the idea that there's going to be some things that inherit, some things that are composed. But what do those terms mean in terms of for within the context of manufacturing data?
Yeah, I think OSI Pi probably does. The asset framework sort of is a great example of inheritance, right? Where you've got templates, and I could have a template that is a production line, right? And then maybe for site, I've got my Charlotte production line, right? That inherits from the global template for production line. Maybe at the global level, all production lines, must have a speed and a speed set point. Maybe at Charlotte, they've got a speed set point, and like a temperature or something, right? I'm extending that template with additional properties as I sort of go down that inheritance tree. Then you can apply those classes or templates onto instances. So if I've got 5 production lines, I could say, hey, you're each a Charlotte production line, right? And you then inherit those properties. So those production lines, all 5, now have those 3 properties because I've assigned that class to these 5 production lines, and they inherit the properties of. So typically, like class, I have a class of something with properties, behaviors, rules. Could be, it's not necessarily limited to properties, but it's sometimes behavior. And then you could have a top level item that inherits sort of down, and then you could eventually apply that into an instance.
Okay. Yeah, I generally do inheritance, like if I'm working with asset models. So I might have just my basic pump, which is telling me I have a pressure and a temperature and maybe a flow. But then I might have other complex pumps that have a lot more information to it. Maybe I'm going to throw in a motor there as well. But if I make a change to that base model, that now gets inherited to every model that's off of that. And it also works really well, like, so I'm a big fan of inductive automation, their ignition product for at the level 2, especially for building, like, since we're talking a lot about UNS for building them, there's parameters that are associated with what they call UDTs, which are these, you can call it a class, if you will, and you can instantiate them, but I can inherit those parameters as well. So if there's certain things that I want to pass through, it makes it very easy to build some very complex models. But the downside of doing that is where we get into the whole composition, because maybe I don't want all of those things there. So how does composition differ, and when do we want to use one versus the other?
You can sometimes inheritance is like very singular, like your instance can only inherit from one template. But when we talk about composition, maybe we have classes that compose of different bits of functionality. So maybe you've got a class for OEE, you've got a class for SPC, you've got a class for vibration analysis, right? And then I have my instances. I'm like, well, this motor has vibration analysis and it has SPC, right, on flow rate or something, right, or some sort of quality point. So whereas, so composition, you can compose all these like classes to bring in certain behaviors and start to apply them to specific instances. You've also got composition from another point of view, I guess, and that's like the data modeling point of view, where you may have entities that only exist in the context of its parent. So there's 2 types of composition. You can sort of do modeling with composition, or you can do like, what would be an example? Like equipment properties only exist in the context of the equipment. You can model and use, compose behavior to generate your final result. So your equipment instance could be composed of multiple classes. That's one way of talking about composition. The other way is in the sort of the way that you model your schema through composition. So, or the way you message through, these data structures. So I could have equipment properties and they only exist in the context of equipment. So temperature 12 doesn't mean anything to anybody, right? Temperature 12 on, pump 1, 1, 2, 3 does mean something, right? So you could say that temperature only exists in the context of the motor through the relationship called composition. The other one to that is an aggregation, where these entities can exist outside of each other. So an example of that could be maybe I've got pump 1, 2, 3, and I've also got maybe a work master, perhaps, right? Where these things can exist independently of each other, but also be related, right? So I could see this work master as an equipment specification, which is that motor 1, 2, 3. So yeah, there's two different types of ways you could talk about composition there.
Yeah, and in some ways, I'll also use these in this data governance concept of, especially when I'm starting to build equipment models of, what do I want to make? We'll call it a folder. So I'll just reference back for people that are familiar with Ignition. Do I want to make it a folder? Do I want to make it a UDT with all these nested UDTs that are part of it? And that's the balance of what do you want to have inherited and what do you want to force and govern, or say you must do this thing, versus here you're going to compose what this, if you're at a work center, you're going to compose what are some of the work units that are associated with that, and what are some of the other, enforced data models that you're going to have associated with it. So, for instance, you were talking about, do I have an SPC measurement here? Do I have an OEE measurement that exists within that? So you can compose it, but once you have those composed, then you can also have different flavors, if you will, of that pump, different flavors of, OEE, those types of things. So, it's one of the balances. So, you brought this word up here. It's called aggregation. And, when I think of aggregation, there's some really great data tools that are analytic tools that are out there. Actually, Flow Software, we had Lenny from there coming in talking about their new time-based historian on one of our time series podcasts. But when I think about what Flow Software does, it's aggregations and event context. So, but in that, for me there, it's I'm now taking some time series data and I'm looking at min, max, average. There's a lot of things I can do. Those are all aggregations that I can add. But what else can aggregation mean within the context of manufacturing data?
Yeah, well, we talk about data modeling aggregations. That's where entities can exist. Maybe it's an aggregation relationship between entities, and they can exist outside of each other. So I could talk about and share information about an equipment, or I could talk about and share information relating to a work master, right? So they can exist separately. So that would be an example of, I guess, aggregation. But then, like you said, you can aggregate data itself, as opposed to talking about data relationships. And min, max, deltas, moving range. That's it. SPC stuff's going back to me.
Oh yeah, there's a lot of things you can do in there. What was the
totals, sums, a bunch of different math.
Yeah, you can do all your rules in there as well, all the Nelson rules of all the various things that occur within SPC. So you have used an ISA 95 term, and in case people that are listening to this aren't as familiar with ISA 95, go back to the very beginning of our podcast. You'll pick up a whole lot about ISA 95. But the concept of a work master, just, since you've used it a couple of times, can maybe you break that down real fast?
Yeah, sure. It is product definition to the level required to make it on site, basically. And when I say product definition, I mean, what are the steps involved? What are the resources? And when I say resources, I mean, people, equipment, physical assets, and materials. And then what's all the steps required to make it? It's that detailed SOP with resources applied.
Yeah, so that is a teaser. It's taken the part 3, the activity models, and then, from the plan, and then what are all the resource models and information models that are associated to get it all the way through, all that level of detail. But that work instructions is a part of a work master, if I have that right. So
it's the detail required to actually make it on site. Whereas it usually relates either to an operations definition, operations segment, or a process segment, depending on where you've modeled your product definition. Usually your ERP system has some sort of concept of how to make something. Maybe it knows you just need a production line and has a BOM. Maybe it could just be one manufacturing process step. Maybe it knows you've got to make and package. Maybe it knows you've got to, mix, bake, package. So it depends on where you put the definition. Do you put it up in your ERP? Do you put it down in your layer 3 space? And then what's that common understanding between business applications and between the business of how to make something? And that's usually your process segment there. But the work definition is, from layer 3 down, like it's the actual detail on how to make it. So you might find it's a one-to-one, work master to operation definition. Maybe it's a one-to-many, many-to-many. It really depends.
Okay.
And sometimes your work masters are also reusable. Maybe you've got like an inspection work master, all right, and you've got 15 different inspections throughout making something. So there's a little level of reusability in that as well.
Okay. Yeah, so just keep on the lookout for some upcoming ISA 95 training we're going to offer. We're going to get a lot into work masters and what that means. And to me, they're one of that's the glue that's just so critical on getting everything. It's like the orchestration of your manufacturing process.
More like the ontology.
Yeah, there you go. Exactly. So, so last word, or just one thing I've noticed, I've used this a lot. It's context, and it's kind of funny that we just throw these words around, and here we are on the podcast. In the context of, so when we say context, in just really from a data standpoint, the thing we always talk about is how we're adding context to the data moving up. So, for instance, if I just have a number. Well, that doesn't mean anything until I give it a unit of measure. Well, that's now adding context. So what are some other examples of what do we mean by that context? So it's within the boundaries or within the frame of this.
Yeah, like you said, it's basically the frame of reference for the particular bit of information, right? So like you said, that data value changing may mean something, but when you add a unit of measure, it means something else. When you associate that with maybe a PNID tag, right, that adds more context. When it's like TI99 and TI99 is part of bioreactor 1, right, that adds even more context, right? Mm-hmm. And then when you add the context that bioreactor is producing something right now, and it's producing in the context of order, PO 1, 2, 3, 4, whatever it happens to be, right? So it's just about adding more context in. Maybe PO order 1, 2, 3 is being made to workmaster, standard widgets 1, right? And standard widget 1 has the context of that temperature should be between 200 and 100 degrees or something like that, right? So there's all these, layers that you can start to, and context, right? And there's this frame of reference under which that value could mean something important or not, right? And that's why we talk about context. So is the value 100 important? I mean, who knows, right? We need more information. We need to know what it actually is, what do we plan it to be, and what is our standard definition of what it should be, right?
Yeah. And in a lot of these, I mean, going back earlier, just to the very first thing we talked about is broker. It's it depends on the context. So in what use or within what capacity are you using this? So I think there's a lot of ways that context can come in. And I mean, even there was a post on LinkedIn a while back about, what does SCADA mean to you? And it's a different thing, if you're in oil and gas versus in a refinery versus in manufacturing, like if you're doing discrete manufacturing, SCADA has very different meanings. Well, it's within the context of what that is. So, it's always one of those funny words we all seem to kind of understand, yet we use it, and we've even used it on this podcast. And here we are attempting to define it. Well, we just know it when we see it, I think. So,
yeah, it's a frame of reference, I guess you could say.
Frame of reference, great adder there for that. So the last thing I want to talk a little bit about is this concept of GraphQL, dgraph. I mean, we hear graph a lot, especially when we start talking data ops and data persistence, and it's these things that I don't know that people rightly understand. That believe this or not, graph and GraphQL are just as different as Java and JavaScript, right? So unpack this for us, Tom. What are these things?
Well, if you're paying attention, GraphQL, that QL on the end is probably, the giveaway there. GraphQL is a query language. That's what the QL stands for, kind of like SQL, GraphQL, right? It is purely a query language. It can sit above different databases, right? It doesn't necessarily have to be a graph database. So typically when people talk about graph and graph structures, maybe they're referring to a graph database. Like there's Neo4j, there's Rhize, there's dgraph as well. But GraphQL is just a query language. So there's nothing stopping me from putting GraphQL on top of a Postgres or a relational database. It is purely a query language. it is nice as a query language. It's as if sort of REST and SQL had a baby, I would say. You can do a HTTP post with your query as the body and get a response, which is really nice. So it works very well with web applications, right? It is JSON forward as well, and so also it works very well with the web. The other cool benefit is that you can navigate relationships very easy with GraphQL. So if I've been in manufacturing for a while now, and doing the reporting side of manufacturing in SQL, you'll end up with these 400 or 500 line SQL scripts just to do your report or get your data structure, right? And you're always limited usually to just one table at the end, right? Here is my final aggregate result. To be these 500 lines, right? In GraphQL, relationships are as easy as just like nesting the values you want within the context of the thing you're querying. So if I want equipment properties, I could just query equipment, and then properties, and on the properties, I maybe just want to get the ID, right? And so you can describe joins really easy in GraphQL, which is really nice. No more left, right, join, inner join, outer join, nested tables. All that kind of falls away because you can just navigate these relationships really nicely. The other benefit is you can describe, like kind of like SQL, you can describe what your resulting data structure looks like. And so you can do like, I guess, if I was to put an equivalent for SQL, you can do like nested tables within your return result. It's a very crude analogy, but hey, give me equipment, give me their properties. Now give me that maybe equipment actuals, their job response, maybe the job order, then the work master, right? So you can navigate all these structures quite easily in a GraphQL query, which is really nice to grab out the data set that you're interested in.
I think the important. Go ahead. I'm sorry.
I was going to say it also prevents overfetching. So in like traditional REST APIs, right? There's usually a standard structure of which it responds with every time. So in like an open API, you'll say, hey, get equipment, here's what you get, right? And you're always going to get that, regardless of only if you needed just that one value or just that other value down there or the third equipment in, right? Whenever you do REST, the sort of the publisher of the data is already telling you what information you're going to get in the format you're going to get. In GraphQL, you can just specify just the fields you want to prevent what they call overfetching.
I was going to say, I think the important thing here is that it's the query language piece. It's just the syntax, or it's how you go about retrieving data that could be in any kind of data set, whether it's Postgres or SQL. It's the language that gets you there, I think, is really the key piece. So you mentioned you don't have to use GraphQL with a graph database. So what is a graph database then? So you mentioned like dgraph and Neo4j. It's in a generic sense, it's a directed graph, but what exactly is it? How is that different, and what does that mean?
Yeah, so in a graph database, we're typically storing the nodes, and then nodes and edges, really. That's the key difference, right? So in a relational database, you've got tables and rows, right? In a graph database, we're storing nodes and edges, right?
Okay.
And we can create, and we can define schemas. You can in sort of graph databases. We do that with Rhize. But yeah, at its core, it's not storing like a table file with rows. It's storing a list of nodes and basically all their attributes, and then the edges. And then you can put data technically on those relationships as well. So you can add weights and things like that, right?
Okay. So, and the edges are the relationships of the data. So, and then one way you have okay. Yeah, perfect. It's, the way it was described to me is imagine you're on a football pitch and you have the the players that are sitting out there, and what's the relationship between all of those players at any one moment in time. And so the player is going to be that is the node, and it's going to have certain characteristics or attributes about that particular player. And then where is that person in relation to the position, in this case, of all the other players there? And then you put in the ball, then you put in the coach, and it just makes it even more challenging.
Yeah. The typical example is like social networks, right? Friends, and you're a node, you're a person, and you've got friends, but you can also create multiple relationships to the same node.
Mhm.
And so it's quite performant in traversing those relationships.
Yeah,
SQL, you've got to do a lot of like joins, so like join, maybe iterative joins, right? Based on the same table. Whereas with graph, you can navigate those structures way more performant than what you probably could with a SQL database or relational database.
Yeah, I mean I think that's where knowledge graphs or the directed graphs come in. It's just that complex relationship where it's, yes, you're a friend of, but you're also a customer of, and then you're also a supplier to, and that's how we define those edges, or what are all the relationships here and how all that stuff fits.
Yeah.
Very quickly you can find out. Remember this old game we used to play about, there's a name of a person that lives on a street that has a particular color telephone. Well, the knowledge graph helps put all these things together.
Yeah. They're in, I think their impedance mismatch is also low, which is a good thing.
Yeah, we're going to talk about impedance mismatch coming up, and why this matters and why it's so important, and some history on what is a directed graph, and maybe we're going to get a little in the weeds and a little too much in the where you have all the people that wear propeller hats, but I think it's a very important. It's very important for us to understand that, because this is something you're going to run into, going back to the episode where we talked about why your backend matters, of the different storage mechanisms of when you have highly complex relationships within data, you have to use certain storage formats like a graph database versus, columnar data and tabular data, or a row-based data in there.
Yep. Yep.
Yeah.
Yeah, finding the shortest path between two nodes as well, right?
Yeah, there's a lot that goes into it, but once you've unlocked that, then it makes it very, very quick and able to retrieve a lot of different data stuff as well. So, so we've covered a lot of ground here in the last hour or so. Any other terms or things that you hear a lot of that, well, I don't know if that really gets used properly, or are there other things that's like, yeah, I don't know what it's, I don't think that word means what you think it means, kind of thing.
Yeah, I had an interesting discussion with a colleague this morning on data calculations in manufacturing, and there was definitely a misunderstanding around that one, around the different types of data calculations you'll do. Sometimes it's just around state, like it's just converting Celsius to Fahrenheit, maybe within the context of a property. Sometimes you're doing a calculation that requires some level of history on other tags or other properties, right? So maybe I want to calculate the rolling average of some particular value and then recalc and republish that. And then other times you're calculating not only history of other tags, but of the calculation itself, right? And this whole concept of like, well, where do these different calculations live within your ecosystem, right? So just the idea of data calcs and just trying to pair out that there is when we say data calculations or data transformations, sometimes they're simple. Sometimes we're talking about just simple math. Sometimes it's a lookup table, right? Maybe we're converting one system's, what would I call it? One system's like enum or enumeration on machine state into another states, or the order status into a different order status, right? That everyone can understand. Sometimes they're simple, sometimes they're complex, right? And knowing the best place to put them is, you can't just generalize and treat them all the same. Basically.
Yeah, exactly. Yeah, what you're talking about, we run into this a lot, is this what's known as sensor to signal. So it's that here's what I'm measuring, but that's not actually the thing that I want. So how do I take the 5 things that I have and slice and dice that in order to get the value or the signal, the thing that I'm actually looking for?
And then then do you want to like persist that? Do you want to backfill persist that? If you change that, what happens? If you redefine that, what happens? There's a lot. That was a little topic that came up just this morning, actually.
Yeah, no, there's a lot that goes into it, certainly in data. But all right, cool. Well, I think we've covered some really great ground here in terms of, let's start defining, or at least describing, what some of these terms are and what we mean by that. But I think really the key takeaway here is that it all depends on the context in which the words are used, but make sure that when a word gets used, we do a level set so that people can at least understand. Let's make sure we're on the same page. So when we're talking about these things, but and hopefully it was helpful to understand what some of these things mean. And of course, going to some of these concepts, they somewhat exist in pairs, is that it's not a good or a bad. It's just there's all these considerations for how you go about going and solving these problems and how you want to deploy the technology in the relationship. So,
yeah, right tool for the right job.
Right tool for the right job. So perfect. Well, Tom, thank you so much again for being on the Rise Up podcast. Look forward to having you back in a future episode. And for everybody that was listening, thanks for stopping by and checking out the defining episode of the Rise Up podcast.
Appreciate it, David. Thanks.